Welcome to today's Explainer. We're diving straight into what I can only describe as a total masterpiece of mathematical education. We're looking at Andrei Petrovich Kiselev's Systematic Course of Arithmetic. Now, originally published way back in 1884, this isn't just some dusty old textbook you'd find in an antique shop. No, this single volume actually fundamentally shaped 20th century mathematical thought. It literally produced some of the sharpest analytical minds in history. And the coolest part? It approaches foundational arithmetic not as a boring chore, but as this thrilling, logical journey. 80 million. Let that sink in for a second. That staggering number represents the pupils who took their very first rigorous mathematical steps directly from the pages of this one book. I mean, imagine that. We're talking about entire generations of students, all united by a single brilliant framework. A framework that taught them not just how to calculate, but how to truly think. And its longevity is just wild. Kiselev's arithmetic enjoyed an incredible 70-year reign as the absolute standard text in classrooms. Just look at this timeline. It survived the fall of the Russian Empire in 1917, weathered 2 world wars, and remained the cornerstone through the entire post-war reconstruction of Soviet education. Think about it. Governments changed, entire empires fell and were replaced, but the mathematics inside this book, it didn't budge. It was just that universally effective. Moving on to Section 1, True Understanding over Memorization. So what made this book so completely bulletproof? Well, it was Kiselev's absolute priority of understanding over memorization. He used this relentless 4-part pedagogy: define, prove, apply, and practice. Now, the absolutely crucial point here is step 2, prove. Most textbooks today, they define a concept, show you how to apply it, and then just throw practice problems at you. But Kiselev, he forced students to actually prove the math first. Because if you skip the proof, you're basically just acting as a human calculator. But if you master that proof, that's when you become a real mathematician. Which brings us to Section 2, the science of counting and discovering numbers. Right from the jump, Kiselev treats basic concepts, like counting, not as assumed knowledge, but as actual scientific discoveries. For instance, when we have a massive number of objects, let's say represented by these abstract vertical strokes, counting them one by one quickly becomes total chaos, right? So what do? We transition to compound units. We count off 10 strokes and group them together, then another 10, and another. And suddenly, we aren't just staring at a random pile of strokes, we've literally invented tens. And when we get 10 of those tens, boom, we invent hundreds. It's this incredibly beautiful, structured progression from total chaos into order. All right, Section 3, Beyond Base 10. Let's look at other numeration systems. Okay, so our beloved decimal system, where we group things by tens, is deeply, deeply tied to our biology. I mean, we have 10 fingers on our hands, right? But Kiselev completely shatters the illusion that this is the only way to count. Let's compare our decimal system with the quinary system, or base 5. In decimal, 10 units make a compound unit of the next place value. But in base 5, a unit of the second place is exactly 5. So to function in a base 5 world, you literally only need 5 digits: 0, 1, 2, 3, and 4. The number 5 in this system is actually written as a 1 followed by a 0, meaning 1 group of 5 and 0 simple units. It completely forces you to uncouple the physical shape of a digit from its innate value. It's a total mind-bender. But what about going bigger? Kiselev points out that a base 12 or duodecimal system is theoretically way more convenient than our base 10 system. Why? Well, because 12 is perfectly divisible by 2, 3, 4, and 6. That makes division an absolute breeze. Whereas 10, it's only divisible by 2 and 5. But, and this is a highly amusing catch, to actually make base 12 work, we would have to invent brand new single-digit symbols for the numbers 10 and 11. Because in base 12, writing a 1 and a 0 literally means one group of 12. Now, to convert standard numbers into these kind of alien systems, Kiselev gives us this highly visual repeated division method. Over here on the left, we're converting the decimal number 1766 into base 5. So we divide 1766 by 5, and we get 353 groups of 5 with 1 unit left over. Then we just keep dividing those results by 5, tracking the remainders all the way down. And if you read those remainders backward, you get 24031. Then, looking at the right side, he converts 121,380 into base 12, using that exact same cascading logic. It's just this beautifully systematic algorithm that completely demystifies how number bases actually work. Next up is Section 4, the logic of operations and the hidden rules. Having built this rock-solid foundation of what numbers actually are, Kiselev then exposes the hidden logic behind operations. Take the commutative property of multiplication, for example. Instead of just dryly stating that 5 times 4 is the same as 4 times 5, he visualizes it as a grid. If you count the grid horizontally, row by row, you are adding 5 4 times. But if you just change your perspective and count that exact same grid vertically, column by column, you are adding 4 5 times. The total number of units never changes, only your perspective does. It is just a brilliant, immediate aha moment.
And this logic builds directly into the associative property, which states that a sum is not changed if we replace several add-ins by their sum. By mastering this, along with the commutative property, mental math becomes highly, highly logical. It's not just some parlor trick. For example, Kiselev notes that if you need to add 68 to 427, you don't sit there struggling with carrying digits in your head. No, you logically alter the add-ins. You add 70 to get 497, and then logically subtract 2 to arrive at 495. You are literally manipulating the building blocks of the numbers themselves.
So, the absolutely crucial point we arrive at here is this. Kiselev's true genius lay in forcing his students to confront the why of math, long before he ever let them use the how. By ensuring that every single concept was derived from first principles, he didn't just teach kids how to sum numbers together. He built impenetrable logical foundations in their minds. He created strong, flexible mathematical thinkers who could adapt to literally any problem thrown their way. Which leaves us with a pretty fascinating thought to close out this explainer. We saw that Kiselev's text survived revolutions, world wars, and regime changes, all because mathematics is absolute. But in our rush toward modern, tech-heavy, app-driven education systems where we so often skip the proofs just to get right to the answers, did we lose something vital by leaving 1884 behind? Perhaps it's really time we re-examine the systematic, rigorous beauty of starting from first principles. Definitely something to think about the next time you instinctively pull out your calculator.